Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the physics series we will be talking about DC circuits. Okay, right, so once again, there's not that many learning outcomes. Hopefully it means I don't have to talk too much. Yeah. Anyways, so the first one is, well, not really something I can really tell out because it's just talking about the circuit symbols. So you know that you had to use a certain symbol to represent a certain thing. Like for example, the light bulb looks like that circle with a cross in it, and then the battery is like one long line and one small line. And of course, the long line is like one of the lines represents the positive, one of the line represents the negative, and there's all these different symbols that you can use. So I don't know, maybe I'll have shown you some of the symbols, but the best place to look at it is your notes, I suppose, your school notes, or you can, search it online and you can definitely find these symbols on the web and use them correctly, kind of. Okay, so the next thing is the next learning outcome is about drawing and interpreting circuit diagrams. Yeah, that's just related to the first one. But the idea is if you see a circuit, you must be able to change that into a diagram. And if you see a diagram, you must be able to replicate a circuit in real life using it. So this will be most applicable to practical because that's where you actually do this. I mean, you can do that in a theory paper, right? Technically. Like you can actually suddenly set up a light bulb and a battery in the middle of your 2 hour paper. But you can do that in practical because you're very likely to actually end up doing that. But in theory, what you do need to do is to understand what all the symbols means, and that's kind of related to the first learning outcome. Yeah. I don't know. I can't really tell much about it. It's just a matter of memorizing and familiarizing yourself with the symbols. So third one is okay, cool. This is actually something I can talk about. The combined resistance of a bunch of resistors in series. So uh right. So if you look at the resistance of certain resistors in series or in parallel, which is actually the next learning outcome, I'll just cover them both at the same time. So the series one is when you are just adding up the resistance, because if you think about it, that from the previous chapter there's one equation where the length of the conductor or whatever it is affects its resistance, right? So the longer it is, the more resistance it has. So likewise, if you think about it, two or more resistors in series is like just having a longer resistor. And that's why when you find the combined resistance, you're actually just adding up the resistance of all of these resistors. And for the parallel, it's a bit different because it's not in series anymore. So as like resistance is kind of like the current sorry, the the V over the I, that kind of thing. And if you know how V and I differ according to series and parallel, it would make sense why resistance differs this way. But the simple way to tell it is that resistance differs such that when they're in parallel, like when they're resistors in parallel, the resistance the reciprocal of the combined resistance is equal to the sum of the reciprocals of the individual resistances of the resistors. Wow, that sounds like a tongue twister of its own. Okay, never mind. But you get the idea. It's not. If you it shouldn't be too hard to remember this. So the reason is because if you're looking at the current, it you know, it's it's kind of like same within the series, and it splits up when you create parallel circuits, right? And for the PD, usually you're looking at the different for each of the things within the series circuit, in the sense, if you know what I mean, right? So from that conclusion you can get how the resistance varies according to series or parallel. So that shouldn't be an issue. Alright, so the next part after the resistance bit is solving problems involving series and parallel circuits for one source of EMF. Okay, so what this means is just you just get, like, using all the knowledge that you know about how the current varies, how the potential difference varies, how the resistance varies for each of the series or parallel circuits, and then you have to actually answer questions about, oh, what is the potential difference of this, or maybe they won't ask you so straightforwardly, but you will know that there's certain information that you need to find out from looking at the circuit, or if you actually need to draw out the circuit before you even solve it, that's possible as well. So you might need to find out a certain value for either the current, the potential difference, or even the resistance of one of the components in your circuit. So that's what you're usually asked to do. So in such a scenario, it would be good to start from the place where you know everything, like what information you actually know, and write that down if you're the kind of person who gets very confused looking at the circuit, I suppose. Like, write it down in the part of the circuit that you think you must write it down. Like, for example, this particular component has this resistance, and this particular um that wire going there has this particular current going through it, in a sense, for example. So you can write that all down in pencil or something, and then proceed to solving it. Maybe that will make your life a bit easier, honestly. Yeah. And then, if you can really look at the one specific resistor first, you can work with the entire bunch of resistors on the series thing. Because if, let's say, there's a parallel, like there's a bunch of parallel wires with various things on each of them, and the resistor is in one of them, but there's some other thing component on that same wire, then you can first work out the overall resistance for that particular line, and then look at the resistance of the actual resistor that you're looking at, in a sense. So you work through based on parallel or series, you can see which works best. And sometimes you can combine the other parts of the circuit into one resistor or something like that to make your life a bit easier when you're solving it. So just that's how you do these kind of questions. There's some simple ways of making your life easier, but it is still hard. Sometimes you get a very weird looking combination, and if it's an MCQ question, I would suggest that you just move on first and then return to it at the end of the paper. If it's not an MCQ question, then I don't know, that would be quite weird actually. They usually ask this in MCQ questions. I don't know. Anyways, just try your best. Yeah, so that's the strategy, unfortunately. Anyways, so the next one is next learning outcome is show an understanding of the use of a potential divider circuit. Okay, so this is where the interesting stuff comes to play, and it's actually quite fascinating if you think about it, and also quite simple once you realize how it actually works. So yeah, potential divider means that you can vary the potential difference of a particular resistor or component in your circuit, I suppose. And so what you do is, you know, how do I even explain this in words? It's so much. Okay, anyways, so what you do is, like, you have one of the components which has a variable resistance, and the other component is a fixed resistor or something, or component or something like that. So the one with the variable resistance would be something like um yeah, those, what's that thing called, the variable resistor. Okay, anyway, I forgot what it's called, but it has a name for it. So you can use that, and then you can change its resistance by, pushing the thing on it, that thing. You can push it from the left to the right, and you can change which part of the wire it touches, right? So that will that will change where the circuit attaches to that particular resistor and where it exits, and that kind of changes the length of wire it goes through before it exits, and that's why the resistance actually changes in the sense. So once you change the resistance of one thing, the the potential difference across it will be different. That means the potential difference across the other thing will also be different, because the overall potential difference is literally the potential difference of each of this added together, in a sense, if you're looking at it in purely a series circuit with only those two things together. So let's say the circuit has like 11 volts, overall terminal PD is level 11 volts, so you won't have to worry about the EMF or the internal resistance and all that. Just look at the terminal PD as, or if you just ignore internal resistance and you just say the EMF is 11 volts, that will be easier. So if it's 11 volts, and then one has 5 and one has 6, you can then change the resistance of the one with 6, like, for example, and you can make it like only take up 4 volts, and then the other one will end up having 7 volts, for example. And how do you do that? Like, you change the resistance, and the ratio of the resistances will actually give you the ratio of the potential difference that you get there. So what do I mean? Let's say if the how do I put it? Okay, yeah. So the resistance the is the PD over the current, and in this case, the current. Wait, what am I saying? I think I'll just write it down. It's easier to write it down, honestly. So yeah, it's kind of like the overall EMF times the resistance of that particular component over the combined resistance of the circuit. I guess that's the easiest way to put it. That's how you find out the actual PD of each of those components. Because it's a series circuit, so it kind of works that way. You can just add up the resistances and not have to worry about it. Anyways, but if you're using a parallel circuit, then you just need to find out what is the so-called combined resistance of the entire circuit, and then you put this in as part of that particular. Like, you have to see how it works. Like, you have to see how this resistance contributes to the overall resistance of the circuit. If it's an additive function, then you can actually do that. If it's not additive, then you shouldn't do it that way. You have to put a different value on top, in a sense. So usually they will you use this for a series circuit, or a circuit where the thing that you're looking at is like the overall structure is series, even though one component may actually just be a parallel circuit all on its own. So that's the general idea. Anyways, so yeah, that's how they make confusing problems, because there's so many permutations and combinations that you can come up with series and parallel, which is just quite annoying, but yeah. Anyways, let's move on. The next one is about thermistors and light dependent resistors. So you can actually use them in potential divider circuits, because instead of adjusting that little tab thingy manually, you use temperature for a thermistor, or the amount of light, like the brightness of light on a light dependent resistor, to adjust their resistance, which will give you the same effect of changing the resistance on a normal variable resistor. So yeah, so the last learning point is potentiometers. Okay, so potentiometer is even harder to describe in words because it's like very weird. like even drawing the circuit out is just weird. So um, basically you're trying to find the potential difference of the two components here. And in order to do that, like we compare the potential difference against this straight piece of wire, which you have a certain length of. And since it's a straight piece of wire, you can assume that equation, the resistance equals that rho L over A. So you can compare the potential difference of whatever that you're measuring with the length of the wire that has about the same potential difference as this object, such that you end up getting zero current. So how do you get zero current? Basically you have a negative current going in one of them, like a current going in one way for one of them and a current going the other way for the other one, and that will give you your opposing current. And if you have just the right amount of opposing current, like they are equal to each other in magnitude, it will cancel out and you have zero current. And how do you measure the zero current? You use an ammeter, like that really, not just any ammeter, but like the really really sensitive version called the galvanometer. And that thing can really notice minute differences in the current, and it will show you when it's zero current. And this, I think, is pretty a decent method of trying to find out the potential difference, or at least compare it. It won't find the absolute thing, but more like you just compare it. You can compare one with the other and then see which one has a higher potential difference or something like that. You can do that, and sometimes you can actually calculate the potential difference. So it's a pretty useful thing to do stuff with using a potentiometer. Yeah, I guess there isn't really much to it, but the place you're most likely to be using this practically is in a practical, obviously, but you might need to draw the circuit for this in a theory paper, but you're more likely to draw in a practical paper, honestly, because you'll be actually doing an experiment with the potentiometer. That is, if you get the experiment. There's only so many experiments they can put in your physics paper, and one of them will be electricity based, and there's so many things you can choose from. This is just one of those things they can choose from. Yeah, if you get this, then good luck. You had to set it up properly, otherwise it will kind of screw up. There's a lot of ways to so-called, what should I say, like there's a lot of ways to mess up, and there's a lot of ways that you had to actually go and check it and then see how to fix that fault, basically. Like see where the troubleshooting. You have to do some troubleshooting in a sense. Okay, I think we're done. Yeah, we're kind of done. So I hope you found this episode useful, and if you did, please press the like button and subscribe. And with that, I would like to say thank you and bye.